In November 2026, Voyager 1 will become the first human-made object to reach one light day from Earth. That means a signal sent from NASA's Deep Space Network, traveling at the speed of light, will take 24 hours to reach the spacecraft, and another 24 hours to hear anything back. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, put it simply: if I send a command and say "Good morning, Voyager 1" at 8 a.m. on a Monday, I'm going to get Voyager 1's response back to me on Wednesday morning at approximately 8 a.m. 2 full days to say hello. That distance, 16 billion miles, is the farthest any object built by human hands has ever traveled. Voyager 1 has been moving away from Earth since September 5th, 1977. It has not stopped. It has not slowed. It has not changed direction. It has not been touched, repaired, or refueled. And while you are watching this, it is still going. Right now. This second, at 38,000 miles per hour, into a region of space where no instrument was designed to operate and no one expected it to survive this long. Voyager 1 was built with 69 kilobytes of memory, 3 million times less than a modern smartphone. Its computers process about 8,000 instructions per second. And yet, it is still alive, still responding, still sending data back to a species that for the first time in its history has to wait a full day to hear from the farthest thing it has ever made. But reaching one light day is not a celebration, it is a threshold. And what it reveals is not how far we have come, it is how far we have not. To understand what one light day means, you first need to understand how Voyager got there. Because Voyager 1 did not reach 16 billion miles by running its engines. It has not fired a main thruster since November 1980. The spacecraft launched from Kennedy Space Center on September 5th, 1977, 16 days after its twin Voyager 2. Its primary mission was to fly past Jupiter and Saturn, photograph their moons, study their magnetospheres, and send data home. That mission was supposed to last 4 years. Voyager 1 reached Jupiter in March 1979 and Saturn in November 1980. At Saturn, NASA faced a choice: send the probe past Titan, Saturn's largest moon, which was known to have a thick atmosphere, or skip Titan and redirect toward Pluto. They chose Titan. That decision sent Voyager 1 upward, out of the plane of the planets, on a trajectory that would never bring it near another world again. From that point on, so Voyager 1 has been coasting. No engine burns, no course corrections. The only thing that ever pushed it was gravity. During its flybys of Jupiter and Saturn, the spacecraft stole small amounts of orbital energy from each planet, gaining speed without burning a drop of fuel. Each flyby worked like a slingshot, the planet's gravity bending Voyager's path and flinging it faster outward. The planets barely noticed. The spacecraft gained thousands of miles per hour. This technique, gravity assist, is what gave Voyager one escape velocity from the solar system entirely. The planetary alignment that made the trajectory possible, with Jupiter, Saturn, Uranus, and Neptune roughly lined up, happens once every 176 years. The window opened in the late 1970s. NASA took it. Since 1980, Voyager 1 has obeyed one law. An object in motion stays in motion unless acted upon. In interstellar space, almost nothing acts on it. No air, no friction, no drag. It continues at 17 kilometers per second, decade after decade, the same trajectory, the same speed, the same silence, and for 48 years we have been listening. But the farther it goes, the harder that becomes. At one light day, listening turns into something else entirely. One light day is 25.9 billion kilometers, 16.1 billion miles, 173 astronomical units. Light, the fastest thing in the universe, needs a full 24 hours to cross it. For perspective, during the Apollo missions, there was a delay of about 2.6 seconds between the astronauts on the Moon and mission control, because the moon is 1.3 light seconds away. That was enough to make conversations feel slightly unnatural. Sunlight reaches Earth in 8 minutes. It reaches Mars in about 13 minutes. Pluto in roughly 5.5 hours. It will reach Voyager 1 in 24 hours, a full rotation of the Earth. The time it takes you to wake up, live your entire day, go to sleep, and wake up again. That is how long a single photon needs to travel from here to there. This is not an abstract number. It creates a real, physical problem. Every command NASA sends takes a full day to arrive. If the spacecraft malfunctions, mission control will not know for a day. Their response will take another day. 2 days of total silence between a problem and any possible fix. Dodd describes this as operating in slow motion. Every decision must be made knowing that its outcome will not be known for 48 hours. In October 2024, Voyager 1's fault protection system accidentally switched the probe from its primary X-band transmitter to the backup S-band, last used in 1981. The team at JPL had to troubleshoot across a gap of nearly 23 hours each way. Each attempted fix required 2 days of waiting. They eventually reactivated the X-band transmitter in mid-November, but the experience confirmed what the team already feared. At this distance, communication is no longer a conversation. It is an exchange of messages between 2 different versions of time. There is no more now between you and Voyager 1, only a delay. And it grows every day, second by second, as the spacecraft moves 3.5 astronomical units farther from Earth each year. But the distance is only half the problem. The signal itself is disappearing. Voyager 1 transmits at 160 bits per second, roughly the speed of a dial-up modem from the 1990s. The signal strength is 22 watts, the same power as a refrigerator light bulb. That signal has to cross 16 billion miles of vacuum before it reaches anyone. It does not bounce, it does not amplify, it does not echo. It simply spreads outward in an expanding sphere, getting weaker with every mile, until by the time it arrives at Earth, it is billions of times fainter than when it left. By the time it arrives, it is almost undetectable. NASA's Deep Space Network uses dish antennas up to 70 meters across at 3 stations around the world. Goldstone in California, near Madrid in Spain, and near Canberra in Australia. Multiple antennas must be combined to gather enough signal to decode. Dodd compared it to hearing someone whisper from the other side of a stadium. Except the stadium is 16 billion miles wide. Deep Space Station 43 in Canberra is particularly critical. It is the only antenna on Earth capable of sending commands to both Voyager spacecraft. Between May 2025 and early 2026, that antenna underwent essential upgrades. During that window, no commands could be sent to either Voyager. Both spacecraft had to survive alone, running on preloaded software and their own autonomous fault protection systems. If anything had gone seriously wrong during those months, there was nothing anyone on Earth could have done about it. The signal is faint, the delay is enormous, and the power source that keeps both alive is running out. Voyager 1 runs on 3 radioisotope thermoelectric generators, RTGs. They convert heat from decaying plutonium-238 into electricity. At launch, they produced about 470 watts. That number drops by roughly 4 watts every year. In 2025, the output is below 280 watts, not enough to power all systems at once. The spacecraft originally carried 10 scientific instruments. Most were shut down decades ago after the planetary flybys ended. By early 2025, 4 remained active. Then on February 25, 2025, NASA powered down the cosmic ray subsystem on Voyager 1. On March 24th, Voyager 2's low-energy charged particle instrument followed. Each probe was left with 3 working instruments. Voyager 1 still operates its magnetometer, its plasma wave subsystem, and its low-energy charged particle instrument. That last one is scheduled to be deactivated in 2026, the same year it crosses the 1 light day mark. After that, 2 instruments, then 1, then silence. Linda Spilker, Voyager project scientist at JPL, said it directly. Every minute of every day, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last. But that day could also bring another interstellar revelation. Each watt lost forces a choice. Each choice eliminates something permanently. Instruments are not turned off because they failed. They are turned off because there is not enough power to keep them alive alongside everything else. No repair, no resupply, no return. The mission is no longer about discovery. It is about keeping the link alive as long as possible. Engineers believe at least one instrument per spacecraft could survive into the 2030s. But they are honest that a 48-year-old machine in interstellar space can fail at any moment without warning. In September 2024, NASA performed a thruster swap on Voyager 1, switching from clog thrusters to a set that had not been used since 2018. In May 2025, the team managed to revive backup roll thrusters that had been unusable since 2004. Everything on board is now single string. There are no more backups. If a critical component fails, there is no spare. And when the last instrument goes dark, Voyager will not stop. It will keep moving. For a very long time. When the final transmission ends, nothing visible will happen. No explosion, no alert, no goodbye. Voyager 1 will stop responding. The Deep Space Network will listen and hear nothing. That will be the end of the conversation, not the end of the journey. The spacecraft will continue on its trajectory indefinitely. The Sun is too far behind and too weak to pull it back. Voyager 1 will drift through interstellar space for millions of years. Its systems dead, its instruments silent, its antenna pointed at a star that will eventually look no different from any other. In 1990, at Carl Sagan's request, Voyager 1 turned its camera back toward Earth one last time from a distance of 3.7 billion miles. The image it captured showed Earth as a fraction of a pixel, a tiny dot suspended in a beam of scattered sunlight. Sagan called it a pale blue dot and wrote that everyone you love, everyone you know, everyone you ever heard of, lived out their lives on that speck of dust. The cameras were turned off after that image to save power. They have never been turned back on. Attached to its body is a golden record, a 12-inch gold-plated copper disc, 115 images of life on Earth, greetings in 55 languages, 90 minutes of music, from Bach's Brandenburg Concerto to Chuck Berry's Johnny B. For Good to Blind Willie Johnson's Dark Was, The Night Cold Was the Ground. And an hour of recorded brainwaves from Anne Druyan, creative director of the project. The recording was made shortly after she and Carl Sagan realized they were in love. She said later that her thoughts during the session were about the history of the planet, what it was like to fall in love, and how it felt to try to capture the essence of being human in an hour of electrical signals. She married Sagan. The record carries her thoughts, compressed into analog data on a disk now 16 billion miles from where she sat. The cover carries a pulsar map showing Earth's position relative to 14 pulsars, a diagram of the hydrogen atom, and instructions for extracting the audio. Sagan chaired the committee that designed it. The record was not made for us. It was made for whoever might find it millions of years from now, long after every circuit on the spacecraft has failed and every trace of plutonium has decayed. A message written with the understanding that nobody alive today will be there to explain it. In about 40,000 years, Voyager 1 will pass within 1.7 light-years of Gliese 445, a small star in the constellation Ursa Minor. It will not stop. A study of long-term stellar encounters calculated that the timescale for a spacecraft colliding with a star is on the order of 10 to the 20th years. Voyager will outlast the Sun. It will outlast most stars currently visible in the sky. It will drift through the galaxy carrying a recording of a human heartbeat long after there are no humans left to have one. But the golden record is not what makes this milestone matter. But what matters is what one light day tells us about ourselves. One light day sounds enormous. It took 48 years of uninterrupted flight. It is the farthest we have ever sent anything, and It is almost nothing. Proxima Centauri, the nearest star, is 4.25 light-years away. At Voyager's speed, reaching it would take over 73,000 years. The Milky Way is 100,000 light-years across. Voyager 1 has covered one light day. 1/365th of a single light-year. If the galaxy were the distance from New York to Los Angeles, Voyager has crossed your living room. The Oort cloud, the outermost boundary of our solar system, begins at roughly 2,000 astronomical units and may extend to 100,000. Voyager 1 is at 173. It will not reach the inner edge of the Oort cloud for another 300 years. It will not exit the far side for approximately 30,000. The spacecraft that has travelled farther than anything humans have ever built is still, by any meaningful cosmic definition, inside our own solar system. It has not left home. It has walked to the end of the driveway. That is what this milestone carries. One light day is not a destination. It is a measurement of how vast the gap is between where we are and where the nearest anything else is. The universe operates on a scale that does not accommodate human lifetimes. Even our greatest engineering achievement, running without interruption since Jimmy Carter was president, has barely begun to cross the distance to the nearest star. The silence Voyager is heading into is not an anomaly, it is the default state of space. We are the exception, and we are very, very small. Voyager 1 was launched with 69 kilobytes of onboard memory, 3 million times less than a modern smartphone. It was built for a 4-year mission to 2 planets. It has been operating for 48 years. It crossed the heliopause in August 2012 and became the first human object in interstellar space. It is still transmitting, still responding, still there. In November 2026, a command sent from Earth to Voyager, one will take a full day to arrive for the first time. By the time the answer comes back, 2 days will have passed. 2 days in which the spacecraft will have drifted another 1.6 million miles farther into the dark, without knowing whether anyone is still listening, without knowing that anything has changed at all. Every year, it loses a little more power. Every year, the signal gets fainter. Every year, the delay grows longer. Eventually, the last instrument will shut down. The transmitter will go quiet. The deep space network will point its dishes at the sky and hear nothing. And Voyager will keep going. It does not know it is alone. It does not know it is the farthest thing we have ever made. It does not know it carries a golden record, with the sound of a human heartbeat etched into its grooves. It simply moves, at 17 kilometers per second in a straight line, through the dark, the way it has since 1977, still going, right now. While you are watching this, extend mission, Earth, light day away, 2026. This science journalist